So we saw that in Fourier series that the multiplication of two periodic signal would result in the convolution in the Fourier series domain. So is there an equivalent of that in the Fourier transform domain? Yes, of course there is, and that's what we'll see now. So let us say we have a signal x of t and y of t. So we'll say that the Fourier transform of x of t is given by x of j omega, which is this equation which we'll repeatedly use often. So this is y of t e power minus j omega t dt. Now when you multiply these two signals, what do we have? So x of t times y of t. Now let us say that we want to find the Fourier transform of this signal. What is the Fourier transform of this signal? It is just x of t times y of t multiplied with one another and e power minus j omega t dt, right? Now what we'll do is we'll just replace this y of t with its inverse Fourier transform. What is the inverse Fourier transform of y of t? It is the 1 by 2 pi integral minus infinity to infinity its spectrum times the phasor. So basically you expand y of t in terms of its component phasors. That's what we are doing here. So let us avoid confusion and then just change this. So these are all variables of integration, okay? So you can name them in any way you want. So we'll bring this 1 by 2 pi outside, it's just a constant. As usual, what are we going to do? We are just going to change the order of integration. If we change the order of integration, then we can have yj nu here and integral minus infinity to infinity x of t e power j. So we have x of t e power j nu t minus j omega t. So we'll rewrite this as minus j omega minus nu t dt. So once we change the order of integration, this is what we do first, and then there is a nu. So what is this? So let us say we'll replace omega minus nu with s. So if we do that, then we get an s here. So what is s? Is omega minus nu. So this is exactly in the form of a Fourier transform, right? So which means now we can call this as some x of js. So we'll just replace this entire thing and say that this is minus infinity to infinity y of j nu times x of js d nu. Now we'll substitute for this s. We substitute for this s, what do we have? We have j of omega minus nu d nu. Now does this look similar to some form that we already know? This is exactly in the form of convolution. This is nothing but 1 by 2 pi y of j omega convolved with x of j omega. That's what we have here. So when you have two signals in time domain multiplied with one another, what happens to their spectrum? The spectrum gets convolved. So if you just multiply two signals, then the spectrum gets convolved. So what does this tell us? What happens to the bandwidth? Because of the convolution operation, remember the length of the convolved output can increase. So in fact, it is equal to sum of the individual lengths, or it can be as much as sum of the individual lengths. So the operation which leads to increase in bandwidth is the product of these two signals in the time domain. So if you take two signals in time domain and multiply, it is possible that you can get at the output frequency components that are not individually present in any of those. For example, let us say x of t is e power j pi t. It has a frequency component which is 1 pi radian per second. And let's take y of t. It has a frequency component, let us say 2 pi t. So if we see the spectrum of x of t, the spectrum of x of t is something which has a line at pi, and the spectrum of y of t is something which has a line at 2 pi. But when you multiply these two, you get e power j 3 pi t, which is at a different location. So the frequency components change, which is different from all the operations that we have seen earlier. So newer frequency components can come into picture when you multiply two signals in the time domain. What happens if you convolve two signals in the time domain? This is something which we have already seen before, and we'll see the extension of that in the Fourier transform now. So we'll try to find out the Fourier transform of convolution of two time domain signals. So what is this? First, let's write the convolution operation. We have x of tau minus times y of t minus tau d tau and its Fourier transform, which is e power minus j omega t dt. What are we going to do? We are going to once again change the order of integration. So we'll just take x of tau outside and just integrate with respect to e power minus j omega t dt. We'll do this integration first. Okay. If we do this integration first, what are we doing? We are trying to find out the Fourier transform of y of t minus tau. We know what is this. Basically, this is a time shifted version of the Fourier transform of y of t. And what is that? That is y of j omega times e power minus j omega tau. This comes from the properties of the Fourier transform, right? So substituting that, we get y of j omega times x of tau e power minus j omega tau d tau. Now the variable of integration is tau, and the y of j omega is completely independent of tau, so we can just bring that outside. So this is all we have. But what is this? This is exactly in the form of the Fourier transform of x. So this is nothing but x of j omega. So we have this to be equal to x of j omega times y of j omega. So this is quite interesting. What this says is the convolution of two time domain signals results in the multiplication of their spectrum. So if we have a signal x of t and it has a bandwidth, some bandwidth b, and another signal y, some other bandwidth v1, now the convolution of these two things will result in a bandwidth which is strictly less than one another. Why is that? Because let us say x of t spectrum looks like this. This is x of j omega, 0. And let us say this is y of j omega, which looks something like this. This is 0. So when you multiply these two signals, clearly only when both the signals are non-zero, only in those locations you will get a non-zero value. In all other locations it will be 0, right? So which means if x had a bandwidth bx and y had a bandwidth by, let us say the product's bandwidth is b, then b has to be less than or equal to minimum of bx and by. This is simply because only wherever they overlap, only in those intervals where they overlap, this product is going to be non-zero, otherwise it's always going to be 0, which means you cannot even produce newer frequency components. The frequency component has to exist both in x of t and y of t, only then that frequency component will be produced in this spectrum, otherwise it will not be even produced. So this is completely different compared to the multiplication operation. Multiplication operation can produce frequency components that did not even exist in x of t and y of t, whereas the convolution operation will produce the frequency components that are only common between x of t and y of t. Okay.